Hello, good morning. Before we step into today's concept, let us quickly reconnect with where we left off. So in previous session, we explored segmentation and swapping. We saw how segmentation allows a program to be divided into logical parts like code, data, stack, making memory management more meaningful and structured. Then we discussed swapping, where processes are moved between main memory and disk to create space, almost like temporarily asking the processes to step aside so another one can run. Now, let me ask you a question. Even after segmentation and swapping, do you think the problem of limited memory is fully solved? What if I told you that like your system can run programs that are larger than the actual physical memory available? Yes, larger than them itself sounds impossible, right? Correct? But this is exactly where we would be talking or discussing in this topic, virtual memory. Let me say again this. Virtual memory is not just a technique, it is an illusion, which we addressed in the previous semester too. Like it is a carefully designed deception created by the operating system. An illusion where your computer makes every program believe that it has access to a huge contiguous or continuous block of memory, even when it is actually not there. And that's why I'm saying unlocking the hidden power behind every modern computer, which is an elegant illusion that makes complex computing possible. So without this illusion, modern computing, as we know, it simply would not exist. Now think about this, like if you open multiple applications, a browser with dozens of tabs, a code editor, maybe a video player, as well as the Zoom meeting at the same time. Now, have you ever wondered how all this fits into memory? And the answer lies in virtual memory. And to implement this illusion efficiently, the operating system uses a powerful technique called paging, where paging breaks memory into fixed size chunks, manages them in a way that feels seamless to the user and to programs. But underneath, there is a lot of things happening. So there are address translation processes, page tables, page faults, moreover, intelligent decisions being made continuously. And in this session, we are going to cover at large how this illusion is created, how paging works behind the scenes, and how the system maintains performance while juggling with limited memory. And by end of this session, you won't just understand virtual memory, but you will see through this illusion. And once you see it, I guarantee that you will never look at your system in the same way again. So let me begin. Now I have like what we saw is the idea of virtual memory as an illusion. Now let's understand why this illusion is even needed at the first place. At the core of the problem is something very simple, but yet very limiting, the physical memory. Let's visualize this. Imagine your computer's RAM as a small, ultra fast bench work or workbench kind of thing, or a table. All your active work happens there only. And every running program, every instruction, every piece of data that needs immediate attention must fit there. But here is a catch. This table or workbench is not infinite. It's a small, it's limited, and it fills up very quickly. Now think about your real usage. You open a browser, then a few tabs, then maybe an integrated development environment, a PDF, a music player, a Zoom meeting, and suddenly multiple programs are competing for that small space. So what happens? When the table gets crowded, performance starts drop. Programs slow down. Some of them begin to lag. and some of them may freeze. And in extreme cases, few of them may crash. Not because the programs are poorly written, but because there simply isn't enough physical memory available to support them all at once. And this is the key point. Like when we say physical RAM is precious, it is fast, yes, but also finite and always in demand. Now let us connect this with what we studied earlier. In swapping, we tried temporarily moving processes out of the disk to free the space. In segmentation, we tried to organize memory more logically. But even with those techniques, one fundamental limitation remains unchanged. The size of RAM does not increase. So the real challenge becomes, how can we run more programs than the memory physically can hold? How can we make the system feel smooth even when resources are tightly used? And that begins us directly to the motivation behind virtual memory. Because instead of increasing physical memory, the operating system does something much smarter, and it changes the way memory is perceived. And that shift in perception is what we are going to explore in this whole session. Now, to get a solution for these problems, like what are listed over here, like when the RAM becomes full, then what physical memory is, let us try to find the solution. And the solution is virtual memory. So we clearly seen the problem now. So physical memory is limited, demand is high, and traditional techniques alone are not enough. Now comes the turning point, the solution. And this is where your OS truly becomes intelligent. At its core, virtual memory is a clever illusion, not a physical upgrade, not an additional RAM, but a smarter way of using what already exists. It makes your computer behave as if it has far more memory than it actually does. Now, some of you might be wondering, how is that even possible? Can we magically create the memory? Or are we really doing this? Not exactly. What the system does is something very strategic. It combines two types of storages: fast memory, that is your RAM, and slower memory, that is your SSD or HDD. And then it blends them together in such a seamless way that the programs cannot tell the difference. Now think of it like this. Imagine your the same table again, the table we were discussing about. Now let us say you are placing a larger storage cabinet besides that table or workbench. Your table is still where active work happens, fast and efficient. But the cabinet stores additional tools, materials that are not immediately needed. So whenever something is required, you quickly fetch it from the cabinet, use it, and if needed, put something else back. To the person working, it feels they have access to a huge workspace. But in reality, only a small portion is actively in use at any given time. And that is exactly what your virtual memory does. It creates the illusion of a large continuous memory space for every program. So each program feels like I have plenty of memory. I can run freely. Even though behind the scenes, the system is constantly managing, shifting, and optimizing the data between RAM and disk. And this is why I'm saying like vast seamless pool available to every program. Correct? So when I say vast seamless pool available to every program, because the program's perspective, there are no limits, no boundaries, no visible constraints. But remember here, this illusion is not simple. It requires continuous coordination. The operating system must decide which data stays in RAM, which data moves to the disk, when to bring the data back, and how to do all of this without slowing down the system. And to achieve this efficiently, OS or your operating system relies on a structured mechanism, a technique that makes this illusion practical and scalable. And that technique is called paging. So we'll break down how paging actually builds this illusion step by step. Because understanding paging means understanding how virtual memory truly works behind the scenes. Now let us understand what exactly virtual memory is doing. Let me make this intuitive. Because the way to truly understand this concept is through a simple relatable analogy. Imagine you are a student working in a library. In front of you, you have a desk. This desk represents your RAM. It is small, fast, and efficient. You can only keep a few books open at a time, the ones you are actively studying right now. If you try to place too many books on the desk, it becomes cluttered, confusing, and inefficient. Now look around you. Behind you, you have a massive library, rows, rows of shelves, thousands of books are placed there, and this represents your disk, your SSD or HDD. It is enormous capacity. It can store everything, but accessing a book from here takes time. You cannot instantly grab everything at once. Now, here comes the most important character in this story, the librarian. This librarian represents the operating system, and more specifically, the virtual memory mechanism. What does the librarian do? The librarian observes what you are currently working on. If you need a new book, librarian quickly goes to the library, fetches it, and places it on your desk. If your desk is full, the librarian may take away a book you are no longer using and return it to the shelf. So from your perspective as a student, you never feel limited. You don't worry about how many books exist in the library. You don't run around searching for them. You simply focus on your work because whenever you need something, it appears on your desk. And this is the illusion of virtual memory. You feel like you have access to unlimited workspace. But in reality, only a small portion is in front of you at any given time. Now let us think a little deeper. What exactly made this system efficient? It's not just library, it's not just desk, it's the intelligence of the librarian, like choosing which book to bring, which book to remove, and when to do it. And this is exactly what your operating system does using paging. It continuously manages small piece of memory, moving them between RAM and disk without you even noticing the same. So keep this analogy in mind as we move forward. Because every time we talk about pages, frames, or page faults, just imagine books, desk, and librarian. And everything will start making perfect sense. Now let's take next step in understanding how this illusion is actually presented to the program. We have been talking from a system perspective, RAM, disk, OS decisions. But what does the program itself see? Every running program is given something called as address space, or what we refer as process address space. Think of this as a private map of the memory. That's what it is says, process said as process address space. A complete continuous view starting from the first address all the way to a very large upper limit. This space is continuous. This space is contiguous, large, and completely private. Private. Each program believes this entire memory space belongs to me. It does not see other programs. It does not see the competition. It does not see the limitations. Even if multiple programs are running at the same time, each one gets its own illusion of memory. Now, here is where things get really interesting. The virtual address space is intentionally much larger than the actual physical RAM. Let that sink in. The program is allowed to think, I have access to hundreds of megabytes or even gigabytes of memory. Even if the system does not physically have that much RAM available at that moment. So what we are doing here is not just managing the memory. We are changing the perception. We are giving every process impression of abundance. No conflicts, no sharing issues, no visible constraints. Now let us connect this with our earlier analogy. Again, imagine the student in the library. Each student is given a catalog, a complete list of all books they could possibly access. Now, from their point of view, it feels like I have access to everything. But in reality, only few books are actually on their desk at any time. And this catalog is the address space. So the address space is illusion of large continuous memory, while the actual data may be scattered, swapped, or partially present in the RAM. Now the big question arises here. If the program is seeing on one continuous space, but the actual data is scattered across RAM and disk, how does the system map one to the other? How does the virtual address space or virtual address becomes the real physical location? And that mapping, that translation is where paging comes into play. And that's what we'll be talking now. Now let us try understanding this core mechanism that actually makes virtual memory work. Till now, we have talked about illusion, perception, and abstraction. But here is where the real engineering begins. The question we left was, a program sees a large continuous address space, but in reality, memory is scattered across RAM and disk. So how do we bridge this gap? And as I stated, answer is paging. Paging is the technique that brings order to this complexity. It takes memory, which could otherwise be messy and fragmented, and divides it into uniform, manageable chunks. Let's break this down step by step. Pages. First, consider the program's virtual address space. Instead of treating it as a huge continuous block, what OS does, OS divides it into fixed size pieces called pages. Each page is a small chunk of the program's memory. Not logical like segmentation, but uniform in size. Think of pages as individual units of memory that can be managed independently. Then comes frames. Now shift your focus to your physical memory, the RAM. RAM is also divided using the same units or same size units. These are called frames. So the pages belong to the virtual memory. Frames belongs to the physical memory. And both are of equal size now. This equal sizing is very important because it allows any page to fit into any frame. Now resize, no resizing is there, no adjustment, no complexity. Third is mapping. Now comes the real magic. The operating system creates the mapping between pages and frames. A page from the program is placed into the frame in RAM. But here's the key. This mapping is dynamic. It keeps changing from as the program runs. At any moment, some pages are in RAM, some pages are still on the disk, some pages may be brought in soon. And the OS continuously decides which page goes where, when to load a page, when to replace a page. Now let us connect this again back to our library analogy. Instead of moving the entire bookshelves, we are now working with individual pages of the books. The librarian doesn't bring the whole book, only the exact pages that you need right now. And this makes the system faster, more efficient, and far more flexible. And most importantly, whatever the external fragmentation problems we talked earlier, paging would be eliminating those external fragmentation problems because everything is uniform. No awkward gaps, no wasted space between allocations. So in one powerful idea, paging achieves efficient memory usage and flexible allocation, as well as the seamless mapping between virtual and physical memory. But then again, this leads us to an even deeper question. If every page can go into any frame and mappings keep changing, how does the system remembers where everything is? How does it translates a virtual address into a physical address instantly? Now, answer lies in the next thing, something called as page table. And that's where we would be understanding what is memory management unit and how paging works. Now let's bring everything together into one powerful flow. Now what we understood was virtual memory creates illusion, paging divides memory into pages and frames, OS maintains this mapping, but there is still one critical question. Who actually performs this translation from virtual to the physical memory? And how does this entire process happens in real time? Now let us enter into memory management unit. At the heart of this system lies a specialized hardware component, the memory management unit, generally referred as MMU. Think of this MMU as a real-time translator. Every time a program wants to access memory, it does not use the physical addresses, it generates the virtual address. And MMU instantly converts that into a physical address. Now let's understand step by step how paging works with MMU. Let's have a walk through the process as it actually happens inside the system. Step 1. Program generates a virtual address. A running program needs data or instructions. So it generates a virtual address with its or within its own address space. And this address space is part of the illusion, not the real RAM allocation. Then comes step 2. MMU breaks this address, takes that virtual address, splits it into two parts, something called as page number and offset. This offset is within the page. This division is crucial for paging. Then step 3, page table lookup. Now the MMU consults the page table. This page table is maintained by the operating system and contains mappings like which virtual page corresponds to which physical frame. If the required page is present in the RAM, is already loaded in the memory, that is step 4A, the memory management unit finds the frame number, combines it with the offset, and generates the physical address. And the data is accessed immediately. Everything feels instant and smooth. Now, what happens if page is not in the RAM? This is called as page fault. If the page is not present, the page fault occurs. This is not a crash. It's a signal to the operating system saying that required page is missing. Please load it. Then OS handles this page fault. The operating system now takes the control. It locates the required page on the disk, finds a free frame in the RAM, Now, if memory is full, it selects the page to remove using a page replacement algorithm. For example, what we are going to discuss later, like first in, first out, least recently used, or optimal. There are multiple algorithms that we are going to concentrate on three. Now, once the page is selected, then it updates the page table. Once the new page is loaded, the page table is updated, the mapping is refreshed, and instruction restarts. The instruction that caused the fault is executed again. And this time, the page is available in RAM. Execution continuously done. Then what makes this powerful? All of this happens in nanoseconds. The program never sees the disk access, the page replacement, and the mapping updates. It simply experiences a large continuous memory space. Let's bring back to our analogy of library last time. So you requested a specific page. If it's already on your desk, you read it instantly. If not, librarian fetches it from the library. Now imagine someone is sitting beside you who instantly knows where every page is and guides the librarian. And that is MMU working with the operating system. So remember this clearly. The operating system manages memory and decides mapping. The memory management unit performs the fast address translation, and paging ensures efficient and flexible memory usage. And together, they may create one most powerful illusion that may be seen in computing. And that illusion is the feeling of unlimited memory on a limited system. While we, while we move forward, one important challenge remains. When memory is full, what happens? Which page should be replaced? Now let us try to understand in detailed manner what is that page table. The page table, as I stated, as translator. To make the paging work, the system relies on this structure. For every process, the operating system maintains a page table that maps virtual page number to its corresponding physical frame number in RAM. Think of it like a library catalog. It does not store the actual data, but tells you exactly where each page is located. The page table plays a crucial role in the system. It enables fast address translation from virtual to physical memory. It tells where a page is present in RAM or not. It helps trigger a page fault if the page is missing. It ensures each process gets its own isolated memory space. So whenever the MMU needs to translate an address, it consults the page table, finds the correct frame, it and completes the process instantly. In short, the page table is the decision maker that connects virtual memory to real memory. Now let us consider two scenarios. Scenario one, I gave name it as page hit. Let's explore this most ideal situation in paging. And this scenario is called as page hit. This is exactly what the system wants to achieve as often as possible. Let's begin with our familiar analogy. Imagine you are studying at your desk in the library. You need a specific page from a book, and when you look down, it's already right there on your desk. No need to call the librarian. No need to wait. No interruption in your flow. You simply continue reading. Now let's translate this into what happens inside the computer system. A program generates a virtual address space. This is a part of its own address space, the illusion of large memory. The memory management unit takes this address, splits it into two, page number and offset. Now MMU checks the page table. It finds that the required page is already present in physical RAM. This is what we call as page hit. Since the page is already in RAM, the memory management unit retrieves the frame number, combines with the offset, generates the physical address instantly. And the data accessed directly from the RAM. The instruction continues execution without any delay. So in this entire process, no disk access is required, no page replacement is needed, no operating system intervention is triggered. Everything is handled directly by the MMU and the hardware. Now, why these page hits are important? This is where your OS performance shines. Because we know RAM is extremely fast, it is directly accessible, and it is optimized for quick operations. So when page hit occurs frequently, programs run smoothly, system feels responsive, and execution is uninterrupted. So when a page hit, what exactly page hit means then? A system has made the right decision earlier. The needed data was already kept in memory. So remember this clearly. Page hit means what? Actually the best case scenario. Fast access, zero delay, seamless execution. Now keep one thought in mind. If page hit is the best case, then what happens when the page is not on the disk? And that situation is called a page fault. And that's where becomes the more interesting and more expensive in terms of performance. This is scenario. Scenario 2, the page fault. Let's see this other side of the story. If page hit is the best case scenario, this is the more complex but completely normal scenario, something called as page fault. Again, let us address that library analogy back. You are studying on your table. You ask for specific page, but this time the page is not on your desk. It is still somewhere in the library shelves. Now, does this mean something went wrong? Actually, no. This is expected behavior. What happens inside the system then? A program generates virtual address. The memory management unit splits it into two, page number and offset. The memory management unit checks the page table. And now comes the key moment. It finds no valid entry up for that page in RAM. And this triggers a page fault. The word fault might sound alarming, but in reality, a page fault is not the error. It is a signal generated. A signal to the operating system that says required data is not in memory. Please bring it. Then what your OS does for this case? Operating system takes the control. It locates required page on the disk, something similar to as a library. It looks for a free frame in RAM. If free frame is available, the page is simply loaded into the memory. And if RAM is full, the OS must choose a page to remove using the page replacement algorithms, which we would be addressing now. First in, first out, least recently used, or optimal. Now, there are multiple other algorithms too, but we are going to concentrate these three mostly used ones. The new page is then loaded into that frame. The page table is updated and execution continues. And the instruction that caused the page fault is restarted. And this time, the page is available in RAM. Execution continues normally. A page fault is slower than a page hit because it involves the disk access now. But at the same time, it is completely normal and expected. In fact, most of the modern systems handle millions of page faults per second. Even we cannot see exactly what is happening in behind the scenes. And they do it efficiently without the user even noticing. Let me relate again back to our analogy. We ask for a book, librarian goes to the shelf, brings it on your desk, maybe replace another book if space is limited. And you continue reading. You don't stop studying. You don't get panic. You simply move forward. So remember, page fault is not an error. It is a routine mechanism that enables virtual memory. So page fault means what? Control delay handled intelligently by your operating system. If page fault happens too frequently, what can it results to? it can result to the system slowing down significantly. And then the real challenge begins. How do we minimize the page faults? Which page should we replace when memory is full? Now let us see how to handle the page faults step by step. Now what we understood was what a page fault is. Let us go deeper and exactly see how the system handles it step by step. Because this is where your operating system truly shows its intelligence. So first, it sends an interrupt to the program. The moment a page fault occurs, the current program is paused immediately. Control is transferred to the operating system. Think of it like you are reading. Suddenly you realize that the page you need isn't on your desk. You pause, call the librarian. Step 2, locate the page on the disk. The operating system begins its work. It searches for the now your operating system begins its work. It searches for the required page on the disk. This could be in swap space or with the file system. So in our analogy, the librarian goes into the library, finds the exact book, and finds the page you need. The next step is find the free frame. The operating system needs space in the RAM. It looks for a free frame. If the free frame is available, the page is simply loaded. If RAM is full, the operating system must remove or evict an existing page. And this is done using the page replacement algorithm. So in your desk, suppose if your desk is full, the librarian removes a book you are not currently using and replaces it with new one. And last step, load the page and update the mapping. Resume execution. So required page is loaded into the selected frame. The page table is updated to reflect new mapping. And this ensures next time when the page is needed, it will remain as a page hit. The interrupted instruction is restarted. And this time the required data is available in RAM. Execution continuously done smoothly as if nothing happened. So even though a page fault introduces a delay, system handles it gracefully and automatically. User rarely notices this. So remember this flow clearly. Interrupt, locate, allocate, load, and resume. And this entire sequence happens in milliseconds. But it is the backbone of virtual memory efficiency. And now the next question is when we have to remove a page and how do we choose the best one to replace? So from CPU to recovery, this is our page fault flow. Now let us compress everything we learned into clear end-to-end flow. This is what happens internally every time. Your program accesses the memory. Step 1 is CPU access. The process begins with the CPU. Program issues a memory request. Virtual address is generated. From the program's perspective, everything is normal. Then comes the MMU check. MMU immediately steps in. It checks the page table, tries to translate the virtual address into physical one. Step 3, if page is missing, then page fault. If the required page is not found in RAM, a page fault is triggered. Execution is paused and control shifts to the operating system. Step 4, your operating system loads the page. Operating system takes over. It locates the page on the disk, finds a free frame or replaces an existing page and loads the required page into RAM. And step 5, your table is updated. Once the page is in memory, page table is updated. The correct mapping is now available and execution resumed. The instruction restarted. The MMU now successfully translate the address and execution continues smoothly. Yes, the page fault handling involves disk IO, which is significantly slower than RAM. But the most important part here is the operating system manages this entire sequence transparently. You don't see the delay. You don't manage the movement. You don't even know what happened. So what is the process here? CPU request, MMU checks, page fault, OS loads, table updates, and execution resumes. And all of this happens so efficiently. And that is your system continues to feel fast, responsive, and seamless despite working with the limited physical memory. And this is the true power of virtual memory in action.